In the last class, we discussed the application of a fully controlled bridge. One of the applications is in dual converter used for drive application, and second application could be in high voltage DC transmission, HVDC transmission. Generally it is preferred for bulk power transmission. Second point that we discussed was the limitations of line commutated converters. We found that power factor deteriorates as you increase alpha. Second major limitation is source current has harmonics. Okay. So the power factor is given by IS1 into IRMS multiplied by the displacement factor. So if I have to improve the power factor, I need to reduce the harmonic content. In other words, IS1 should be approximately equal to IRMS itself, and second one should be displacement factor should be unity. In other words, conduction should start at the positive zero crossing. Okay. Now let us see how to improve the power factor. Before discussing this, we will find out the effect of harmonics in the power transmission or on various equipments. Consider this single line diagram. Power that is generated at a relatively a low voltage, or I can say it as a medium voltage. It could be of the order of 16 kV or 11 kV. Okay. It is stepped up to a very high voltage, either 220 kV or 440 kV. Power is generated at medium voltage, transmitted at high voltage. It is received at the receiving station. Voltage is reduced here using a step down transformer, and it could be further reduced before distributing to other loads. Okay. So you may have more than one transformer. Okay. Consider the high power loads being fed from a medium voltage. Okay. All these loads are connected to somewhere at the common bus, or this point is known as point of common coupling. Okay. One of the loads is being fed from a power electronic equipment. Okay. So if I draw a single line diagram starting from distribution system to the load, here it looks like this. I am considering voltage at the secondary of the transformer is a pure sinusoid. Okay. This is the system impedance. Okay. Could be including the leakage resistance of the leakage impedance of the transformer, and here are the loads, this one being the harmonic producing load. With the moment I am feeding it is through a power electronic equipment, there are going to be harmonics. Now what happens now? Current that is drawn by this harmonic producing load flows through the system impedance. Okay. Even if I assume this to be a sinusoid, because of this system impedance, voltage at this point gets distorted, because current is non-sinusoidal now. So voltage drop across this impedance is going to be a non-sinusoidal. Voltage at PCC is difference between this and this voltage, so this is going to be a non-sinusoidal. Okay. Mind you, all our assumption so far is that input voltage to the bridge is a sinusoid. Now we found that because of the system impedance, the input voltage to the bridge itself may be a non-sinusoid. Here is a 3-phase bridge, is pure sinusoid. I have neglected the resistance here. I am assuming load current to be constant and ripple free. So each device conducts for 120 degrees, source supplies power for 240 degrees. If I assume I naught to be constant and ripple free, source current is going to be a square wave. Okay. Yeah, I have shown here is going to be instantaneous rise. Because of the source inductance, it may not rise instantaneously. Okay, let us not bother about it. The harmonic spectrum of the source current is given by this equation. I said 3-phase 3-wire system, we can have only 6 and plus or minus 1 harmonics. In other words, fundamental, 5th, 7th, 11th, 13th. You cannot have triple harmonics, you cannot have DC also in a 3-phase 3-wire balance system. Okay. So since there is going to be so this current is flowing through the inductance, so there is no di by dt. Okay. Whereas here there is going to be a di by dt. There is going to be a di by dt here. So because of this, the input voltage to the bridge is going to be a non-sinusoidal one. In other words, it has notches. So these are the notches because of di by dt at this instant. Okay, these are the notches. So source voltage has notches, source current has harmonics. What are the effects of harmonics on other equipments that are connected to the power system? I told you that only the sinusoidal or fundamental component of current and voltage are responsible for power transfer. Other components give rise to additional I square R losses, only heating. Okay. These currents will flow through other 3-phase motors. They produce their own rotating magnetic field. Hence they produce a torque which is going to be pulsating in nature. So torque pulsates. If torque pulsates, speed also may pulsate. In addition, they produce noise. Okay. What happens in transformer that are connected in the power system? Additional noise, high frequency noise and heating, because harmonics are flowing, I square R losses are increasing, therefore heat. Now I need to cool the system, my cooling requirement also increases. What happens in cables? That current has to flow through cables. In all the metropolitan cities, power is being fed through cables. Or in an industry, power is the ME motor, the medium voltage motor may be fed from a 6.6 kV switch gear. It will be located at inside the turbine building, and motor may be located few hundreds of meters away. Okay. Now cable has to carry the harmonic current. It gives rise to additional heating. What happens in a power factor correcting capacitors? I tell you, power factor correcting capacitors, they are supposed to carry only the fundamental component or the reactive component of the supply current. Okay, the frequency is same as that of the supply voltage. Okay. And ideal capacitor exists only in the textbooks or in the blackboard. In reality, you cannot have an ideal capacitor or an ideal inductor. So how do I represent a non-ideal capacitor? A non-ideal capacitor can be represented by an ideal capacitor in series with a small resistance, what is known as effective series resistance. R is very small. Another way is to connect a very high resistance across the capacitor. Now for this case we will represent a small resistor in series with an ideal capacitor. This ESR or effective resistance represents the dielectric loss, the contact resistance and other losses. And we all know that dielectric material is a very poor conductor of heat. The high frequency current that are flowing through the line will face a low impedance path through the capacitor. In other words, it is better for the system, because the high harmonic currents, since as the frequency increases, capacitor offers a low impedance, so these currents will flow through the capacitor. In other words, it is better for the system. But then what happens to the capacitor? In addition to the fundamental component, the reactive component, now it has to carry the high frequency current. Therefore, RMS value of the current that is flowing increases. If RMS value of the current that is increases, I square R losses also increases, where R is the effective resistance. So loss increases. Dielectric material is a very poor conductor of heat. It does not radiate the heat very effectively, so temperature rise, and therefore power factor capacitors may fail. Okay. The last one is electronic equipments. Okay. We found that the source voltage itself has notches. Okay. Now your control circuit may sense that this is a zero crossing. This may be zero crossing. Actually, there is one zero crossing here, and if the notches, if the system impedance is high, it may become zero here. Instantaneous value may become zero, and your control system says that is another zero crossing, and it takes some other action. So therefore, your control circuit may maloperate, as well as relays also connected to the system may maloperate. Okay. These are the effects of harmonics. Okay. Let me tell you one thing, there are various agencies or IEEE plus IEC, International Electrotechnical Commissions. They impose specific limits on the level of current, harmonics and voltage notches. Okay, gone are the days like I will design a system and I will use it. What happens to the system is not my headache. Okay, those were the good old days. Now there are various agencies will enforce certain norms. The philosophy is if you are generating harmonics, you do not transmit them to back to the source and affect the other loads. You better take care of the harmonics that you have produced. That is the philosophy. In other words, voltage at the point of common coupling should not get distorted. Okay. Now then, see, if you see in the equivalent circuit, if I have a very stiff system, in other words, this impedance is very small, or in other words, if it is 0, I can allow any amount of harmonics, because impedance itself is 0, voltage at this point is still going to be a sinusoid. Okay. So as the impedance increases, the current harmonics, magnitude of harmonics also reduces. So in other words, the harmonic content that your load can dump to the system depends on the short circuit capability of the source. Okay. So if the system is stiff, harmonic content can go up. Okay. Okay. So basically this power quality or the harmonic content of various standards is a subject by itself. I just give an example, say IEEE 419, so similar to IS Indian standards, there's IEEE 519. What it says is if the bus level is 69 kV, the maximum individual harmonic content should be less than 3% and maximum total harmonic distortion is 5%. So if you have a 6 pulse converter feeding a load whose current is constant and ripple free, and if it is fed from a medium voltage or if it is run from a 69 bus, you cannot be able to energize your bridge, because we found that in a 6 pulse converter, if the current is constant and ripple free, THD is of the order of 48%. Okay. But then now, how do I reduce the harmonics? Because I have to, my application requires AC to DC power conversion. In the same, voltage has to be varied over a wide range. Suppose my DC motor has to be fed from a power electronic converter, voltage has to vary over a wide range to vary the speed. So I have to introduce alpha, harmonics will be there. What is the solution? Now we will start from using the low pass filters, or using the passive components. Can I use a low pass first order filter? You cannot use it. Why? A low pass filter, if I use a first order low pass filter, is nothing but a RC. R comes in series with the line, or R comes in the path of main power flow, and capacitor connects in parallel. You cannot connect a resistor in the path of the power flow, because there is going to be additional I square R losses. So first order filter is ruled out. Can I use a second order filter, a LC filter? By the way, what is the response of frequency response of a second order filter? Gain is approximately constant till the cutoff frequency, or in other words, at cutoff frequency gain falls to 7 times, and above omega c the frequency responses or gain falls at the rate of 40 dB per decade. Okay, so here is the response of a frequency response of a second order filter, LC filter. Gain starts falling, it is 7 times omega c and is minus 40 dB per decade. Okay. So in a single phase system, predominant harmonic is third, so therefore the frequency of the third harmonic is 150, next is fifth, maybe 250, whereas in 3 phase 3 wise system I have fifth and the seventh. These are two major, afterwards 11th and 13th, they are higher frequencies. So I need to filter in a 3 phase case a 250 hertz harmonic and a 300 hertz harmonic. These filters should provide a low impedance path for only these harmonics and should not attenuate the fundamental. Okay. In other words, gain at 50 hertz should be 1 and gain should be 0 at 250 hertz, and for another filter is 350 hertz. Okay. I will repeat, the filter should not attenuate the fundamental component, and it should block completely the 5th harmonic, the 7th harmonic, 11th harmonic, 13th harmonic, and so on. Okay. So is it possible if I use a second order filter, or even if it is possible, what happens to L and C? Omega C is given by 1 over root LC. So as omega C increases, a size of L and C decreases. In other words, size of the passive components that are required to filter the 5th or a 7th or a 3rd is very high, size is very high. In other words, the system will become very bulky, very bulky. Therefore, bulky occupies large space, cost and what not. Another thing, I just asked you the question, blocking completely 50 hertz, sorry, I will repeat, blocking completely the 250 hertz component and supplying 50 hertz component without getting attenuated by a second order filter. I request you to go back to your room and check. You see here result. The gain should be 1, for 50 hertz somewhere here, and for 250 hertz it should be 0. Is it possible? In other words, it may not be possible, So in order to make the system less bulky, or in order to reduce the size of L and C, somehow I need to, or I should increase the frequency of the harmonic that has to be filtered. Okay. How do I do that? By the way, how many pulses are there per half cycle in all the converters that we studied so far? There is only one pulse in 180 degrees. There is only one pulse. So there is an important result which I am not going to prove, is that if there are large number of pulses per half a cycle, the frequency of the predominant harmonic can be increased. This is a very important result. Okay. What it says is, as you increase the number of pulses in half a cycle, your frequency of the predominant harmonic that is present in the line is decreases. Okay. This could be proved using Bessel's functions. Okay. If you have time, you derive it, you go and find out. If you do not have time, you just accept it. Okay. So this is for a line commutator, a half controlled bridge for alpha to pi, and if it is a fully controlled bridge, alpha to pi plus alpha. So instead of having only one pulse, I will chop it into large number of pulses. I will have large number of pulses here. Okay. So I can reduce the harmonic content. In other words, I can improve the harmonic spectrum, or I can increase the frequency of the predominant harmonic. Also, see here, conduction starts at alpha. Okay. So displacement factor now is proportional to, or it is a function of alpha. For alpha by 2 for half controlled, and is alpha for fully controlled bridge. So if I have to improve the power factor, I need to make this alpha is equal to 0. Conduction should start at the positive 0 crossing. I am reducing the harmonic content, in other words, I am reducing the THD. So in other words, what it implies that my fundamental component is same as IRMS, I am improving the power factor. So maybe killing two birds using one stone, maybe because I am starting the conduction at the positive 0 crossing, displacement factor becomes unity, I have a large number of pulses. So in other words, the total distortion comes down. If the total distortion comes down, power factor improves. So, at what cost are we doing this? Harmonic content is also reduced, power factor is improved. At what cost? Nothing comes for free. Okay. At what cost are we doing this? Or what modifications do I need to make in a very rugged off controlled or fully controlled bridge? SCRs are very rugged. Okay. What modification do I need to make to achieve this? Okay. By the way, I said number of pulses, as the number of pulses increases, frequency of the predominant harmonic increases. But I never spoke about the magnitude of the predominant harmonic. It so happens that the magnitude of the predominant harmonic also gets amplified. But then filtering a high frequency component becomes easier. Okay. I told you, because size of the passive component that are required to filter the high frequency component reduces. Okay. Omega c is 1 over root LC. As the omega increases, LC should come down. Okay. Now coming to the question, how to achieve this, have a large number of pulses, how do I achieve, or what modification do I need to make in a fully controlled bridge or off controlled bridge? A fully controlled bridge, T1 and T2 are triggered in the positive of, T3, T4 are triggered in the negative of. The conducting thyristor is turned off by the triggering the incoming thyristor. Let me tell one thing. Okay. Is when T1 was conducting, triggering T3 in the negative of, okay, will apply a negative voltage across a conducting thyristor T1, and T1 turns off. We called it as the line commutation. Sorry. See this figure, in the positive half you have triggered T1 and T2, potential of A is higher than potential of B in the positive half. So when T1 is conducting, cathode potential of T3 is same as potential of A, and okay, a negative voltage appears across T3 in the positive half. Okay. So having triggered T1 in the positive half, you cannot trigger T3 to turn off T1. Okay. See, I told you, you need to have a large number of pulses here. Okay. Definitely looks like a device is turned on at this point and device is turned off at this point. There are a large number of pulses. Zero current implies devices are off, or source current is 0, it implies that power source does not supply power. Current may be freewheeling in the load, that is okay. So device must be turned off at this point when the current becomes 0. So in this bridge, in the positive of T1 and T2 were triggered, now I have to turn off these two, but then I cannot turn off these two in the positive of by triggering T3. In other words, I cannot even trigger T3. So forget about the question of turning off T1. Okay. So looks like I cannot use the force thyristors in a line commutated bridge, or line commutated bridge cannot be used as it is to have large number of pulses. By the way, instead of applying a line voltage itself to the conducting thyristor, I can have additional circuitry, okay, which is having L, C and maybe a voltage source. Okay. So whenever I want to turn off the thyristor, the conducting thyristor, I will energize the separate circuit, that so called the auxiliary circuit, that will apply a negative voltage to the conducting thyristor and it turns off. Okay. This commutation is known as the forced commutation. Okay. We may not discuss the forced commutation because those all are outdated topics. Now there are better methods, better devices are available. Okay. The problem with SCR is you cannot turn it off using gate, but then there are devices which can be turned off using gate. They are known as self-commutating devices like GTO, BJT, IGBT, IGCT. Okay. So to have large number of pulses per half cycle, I need to use the devices which have gate turn off capability. In other words, I have to use the self-commutating devices. Okay. This option is a bit elegant, okay, compared to using an external circuitry to put off the conducting thyristor. This is elegant and maybe a bit expensive. The first one is, since I have to use an auxiliary circuit, my size increases, cost increases, and it is noisy. So the present day the trend is to use the second option, using the self-commutating devices. Mind you, there is a catch here. You just cannot use the self-commutating device directly in AC supply. They should be able to withstand the negative voltage. Okay. I told you that, say 1000 volt BJT may be able to withstand 1000 volts, but then it may not be able to withstand 1000 volts in the reverse direction. Okay. Because base emitter junction is highly doped, so it breaks down faster. So if it is 1000 volts in the forward direction, negative may be of the order of 25 to 50 volts or so. So the device that has to be used in AC should withstand or should be able to withstand the negative voltage, because at every half cycle the input reverses. I have been saying that we should have large number of pulses per half cycle so that the frequency of the harmonic increases or THD improves, but I never said or I never told you anything about the width of the pulse, whether the pulses should be of equal width or when to turn them off, when to turn on the device and when to turn it off. I never told. Or in other words, how do I determine what should be the number of pulses, or what is the criteria to determine the number of pulses? When to turn the device on and when to turn it off. The device turning on or off can be determined using what is known as pulse width modulation techniques. I will repeat, pulse width modulation techniques, PWM, pulse width modulation technique. There are large number of pulse width modulation techniques have been reported in the literature, large number. Okay. The very simple method is the sinusoidal PWM technique. Sinusoidal PWM technique. Okay. What the technique says, if there are n number of pulses, the frequency of the predominant harmonic is going to be n plus 1 into the supply frequency. In a sinusoidal PWM technique, if there are n number of cycles per half a cycle, remember n number of pulses per half a cycle, frequency of the predominant harmonic is n plus 1 times the supply frequency. Okay. So as the number n increases, the magnitude of the lower harmonic reduces, in some cases it may become 0. I said magnitude of the predominant harmonic may increase, yeah, it will increase, but then that can be filtered out easily, because now the omega c, or the frequency that is frequency of the harmonic that has to be eliminated, is very high. So I need to have a very small size of passive components. Okay. So in sinusoidal pendulum technique, I need to have two waveforms. One is a full wave rectified sine wave whose frequency is same as that of the supply wave. In other words, the input supply should be rectified, a full wave rectified. Okay. This waveform is known as the modulating wave. Okay. What is the modulating wave? Is a full wave rectified sine wave. Okay. Having same frequency as that of the supply, but then magnitude changing. Okay. You can get this waveform by just by rectifying, stepping down and rectifying using a diode bridge. And second is a high frequency triangular wave of fixed amplitude and fixed frequency. Okay. So triangular wave, the magnitude is also fixed, frequency is also fixed. Okay. This frequency is much higher compared to that of the supply frequency. How high is that high? We will see sometime later. Whereas the modulating wave frequency is same as that of the supply wave, magnitude controllable. Okay. These two waveforms are compared using a simple op-amp. Intersection of the sine wave with the triangular wave will give you the triggering instant or the switching instant. Intersection of the modulating wave with the high frequency triangle will give the switching instants. Okay. See here, I have rectified a step down version of the supply voltage, okay, which is known as the modulating wave. Amplitude is continuously changing, or magnitude should be variable. Why? We will see later. High frequency triangle, both magnitude as well as frequency is the same. Intersection will determine the large switching instance. By comparing a sine wave and a triangular wave, I got a large number of pulses. How do I distribute these pulses to S1 to S4? Okay. Now I am calling the bridge as S1 to S4. So far I called T1 to T4. Okay. S1 implies a controllable switch or self-commutating switch. Okay. Self-commutating switch. By the way, we know that alpha is measured with respect to the positive zero crossing. In other words, this modulating wave should be synchronized with the supply voltage itself. So there are various ways to generate this sine wave. If you are using a step down version and rectifying it, then there is no problem. The problem starts if you use other means to generate a sine wave. Okay, you cannot just take an arbitrary sine wave of same frequency. Say you can say that supply voltage is 50 hertz. So here is a signal generator which generates 50 hertz. I will take the sine wave and compare it, and these are the switching instants. Fine. But then what is the relationship between this sine wave which is generated by the signal generator with the supply frequency? In other words, they have to be synchronized. If you synchronize them, it's fine. Okay. So, how to distribute? In a bridge, in the positive half, if I trigger T1 and T2, source supplies power to the load. In the positive half, T1 and T2 on, source supplies power to the load. Okay. So, if I keep S1 and S2 on, current is being established in the load. Okay. So, at this instant, I will turn S1, S2 on, assuming that this is a positive half cycle. Okay. For this duration, S1, S2 should be on. Source supplies power to the load. Depending upon the load, current starts flowing and current may build up. And at this instant, now the PWM technique says you turn it off. Okay. Can I straight away withdraw the gate signals to the self-commutating switches so that they turn off? Yeah, you may be able to do this, provided there is a freewheeling diode. Okay. It's a freewheeling diode. Because having established the current in the bridge or in the load, you just cannot open S1 and S2. Okay. Say S1 and S2, something like this. Had closed S1 and S2, source supplied some power to the load, I have established the current. I just cannot open S1 and S2. If I do this, I am breaking an inductive circuit here, because I assume that current to be constant and ripple free, same assumptions that we made for the SCR bridge or fully controlled bridge. Okay. So, if I am opening S1 and S2, I have to provide an additional path for the current to flow. Okay. But the control scheme or the switching technique says that open S1 and S2 now. So, if I open an S1, S2, either have a freewheeling diode across the load, because the moment I open S1, S2, current freewheels to the load, it was flowing in this fashion, now it will flow through the diode, what is known as the freewheeling path, or what I will do is, I will not open S2, I will open S1 and close S3. Okay. What I will do is, in this instant, when the device to be turned off, what I will do is, I will open only S1, I will keep S2 closed, and while opening S1, I will close S3. Okay. So, current will freewheel through S2 and S3. Okay. So, in the positive half, what I will do is, I will permanently close S2 whenever I want to supply the power to the load, or whenever the control circuit says that supply power to the load, I will close S1, and when the device has to be turned off, I will open S1 only and I will close S3. So, trigger pulse sequence for S1 and S3 should be complementary in nature. Okay. The pulses for S1 and S3 in the positive half should be complementary in nature, and S2 is closed for 180 radians, entire positive half. Okay. Why entire positive, why only positive half? Because first thing is I have to, the conduction should start at the positive zero crossing. In other words, T1 and T2 should start conduction in the positive half, or S1 and S2 should start in the positive half. So S2 I will close it for the entire pi radians. In that case, now what will happen? A displacement angle becomes 0, displacement factor unity. So there are large number of pulses. S1 should be turned off now. I will open S1, close S3. Okay. So this has to be complementary. What will happen in the negative half? Same thing. The negative of S3, S4 should be on. S3, S4 should be on. Only then source supplies power to the load. Okay. I just cannot open S4, S3. Now what I will do is I will close S4 permanently for 180 radians. So whenever I want to open S3, I will close S1, open S3. Okay. So now the current freewheels through load S4, S1. Okay. S4, S1. So this is the control strategy. See, here are the waveforms. Okay. Input voltage Vi, I have rectified it. Okay. This waveform I compared with the high frequency triangular, had a large number of pulses. Somehow in the positive of set S1 and S2 should be on to supply the power. So I kept S2 on for pi radians, triggered on and off several times. This depends on the pulse width strategy. Okay. So whenever I am closing S1, S3 is off, and whenever I am opening S1, S3 is on. Same thing is happening to the in the negative half, or from pi to 2 pi. How does the output voltage look like? Whenever S1 and S2 are on in the positive half, output voltage is same as input voltage. Okay. So when S1 is opened and S2, S3 are on, load voltage is 0, freewheeling period. Okay. Waveform is very simple. When S1, S2 are on in the positive half, input voltage is same as the output voltage, and when S1 off, S2, S3 on, load voltage is 0. So it's nothing but a sinusoid, a chopped sinusoid. S1, S2 on, this is the freewheeling period, S2, S3, again S1, S2 on, or in this period somewhere here S1, S2 on maybe, and so on. So output voltage, a chopped sinusoid. This is the freewheeling period, this is the powering period. Same thing happens in the, from pi to 2 pi, here S4, S3 on, and in this region S1, S4 on. How does the source current look like? Same philosophy. I have assumed the current to be constant and ripple free. Okay. So when S1, S2 on, load current is same as the source current, and during freewheeling period source current is 0. Okay. Current freewheels through S1 and S4 in the negative half, or from pi to 2 pi S1, S4, and from pi to and 0 to pi it is S2, S3. Okay. So this is the freewheeling part, current is 0 here. Okay. So source current is also having large number of pulses. Mind you, these pulses are continuously changing. Okay. Because if you see these pulse widths are continuously changing here. Okay. We have at somewhere near the zero crossing, I have a very narrow pulse. As omega t increases, this pulse width increases. So, pulses are sinusoidally changing. Pulses are sinusoidally changing. Mind you, this should be symmetrical. Okay. So, hence the name pulse width modulation technique. Pulses are continuously changing. Now, how to choose the number of pulses per cycle? Okay. How to choose the number of pulses per cycle? Number of pulses per cycle depends on the frequency of the carrier or frequency of the high frequency triangular, okay, which is also known as the switching frequency. The devices are switched at the frequency which is equal to the carrier frequency, remember. Okay, in pulse width modulated inverter or converter, the devices are switched at a frequency which is equal to the carrier frequency if I use a sinusoidal PWM technique. Okay. I told you that if there are n number of pulses for half a cycle, frequency of the predominant harmonic is n plus 1 into the supply frequency. Okay. So, therefore, as n increases, frequency of the predominant also increases, easier to filter. But then as n increases, n implies the number of switchings, so many times I have to turn on and off the switches. Okay. So, as n increases, I have a large number of pulses, so I need to have a fast switching devices, Let me tell you one thing, IGBT may be a fast device, but then if I use it for a high power application, in high voltage application, high power, high voltage, high frequency from a device is just not possible. Yes, in principle IGBT may be a high frequency device, but then if I am using it in a high voltage circuit to transmit high power, my switching frequency comes down. I can't operate it at a switching at a very high frequency. It all depends on the power level, voltage level. Okay. So, one criteria is I need to have a faster switchings. As I switch the devices, switching losses are taking place. Okay, switching losses are taking place, or turn on loss and turn off loss. So, the inverter efficiency also comes down. Okay. As the losses increases, the cooling effect or the heat sink requirement also increases. Okay. Efficiency comes down. Okay. So, efficiency as well as the power, that is the converter handles, will determine the frequency. Okay. In other words, I think the first criteria is voltage and power, that will decide the number of pulses. Yeah, more about it we will discuss in the next class. Thank you.